Hey guys, welcome to Chapter 17, Sampling Distributions. So, I'm going to start off by telling you a story, but before I do, just know that this chapter can get a little crazy in theory in terms of like what it is we're actually doing. Just know that this is kind of building the groundwork for a lot of the calculator work you guys will be doing for the rest of the year. So, a lot of this chapter is kind of just setting up an understanding of why your calculator will work for the things we will do later. So, don't freak out. That doesn't mean you're about to get overwhelmed. But if you feel like, why the heck would you want to do the things we're about to do? The reason is that it's going to be needed mathematically for the things that we'll have to do for the rest of the year. Cool? So, to launch into chapter 17, I'm going to start off by telling you a story. And in that story, I'm also going to flex my amazing Google Sheet skills. There once was a West High group of seniors. The seniors ended up being 92 by the end of the year, 92 seniors. And Mr. Newton was able to collect the ACT scores of all 92 of these students. All right. Now, Mr. Caproni wanted to do a project that was going to require students to find the average ACT score of the seniors at West High. So, Mr. Caproni had 10 students. He told the students that he knew it would be impossible for them to get the correct ACT score for all 92 students. So, what did he do? He asked each of the students within the senior class and write down their ACT scores. All right. So the students go out and do it. Now, I'm going to flex here. I've written a program that when I put that program in, it is going to actually give us a random 30 numbers from this list. Now, notice it does go to 31, but that's because the first line is taken up by student A. So student A has now chosen a random 30 students from all of the kids in the senior class. Student B is going to do the same thing. Student C, D, E, F, G, H, I, and J. J. Okay, I don't like how the first numbers are off to the side of it, so I'm going to go ahead and realign them just because that makes me happy or something like that. So the 10 students got their 30 kids each. All right. Now, notice, would that mean that all of these would have their own 30? No, because 10 times 30 would be 300 students, and there weren't 300 students. So some of the students will have an overlap, like some of them will have asked the same person, but that's okay. But overall, each of the 10 have chosen their own random 30. All right. Then Mr. Caproni said, all right, I need to know the average ACT score of the senior class. So each of these students are actually just going to find the average of their 30. All right. Now, how can we do this? You can actually just go ahead and type in equals average, and you can find the average of the row above that one. All right. And I can do the same thing here again, equal average, and we'll find the average of the row above that. Except we don't want that guy. There we go. And we can continue to do this for all of them. A quick way to do that is just to draw the corner down here, and it will actually do the same formula across the board. Now, notice, a lot of these people got different averages, all right? So student A got 15.7, student B got 16.5, we had a 15.6, 15.03, 14, 15, 15, 15, 16, 15. Now, it may seem odd, like if these were grabbing from the same group of 92, why'd they all get different means? Well, obviously, they had different kids from the 92. So maybe you were like this person right here in the D column, so that was student B, and they got a super high one of 16.5 because they ended up just picking students that tended to have a higher ACT score. Whereas this person with the 14.3 had kind of not as good of students that they chose, so theirs ended up being lower. Is it possible for them to have somewhere of a range of 14 to 16? Absolutely. That's only off by 2 points. And you can see some of these scores are as high as like 26 or as low as like a 12. So it's possible that they would have had different means. All right. Now, this group right here actually makes up its own like set of numbers. So whereas each student had a group of 30 kids that they found their average, me as Mr. Caproni, I have a group of 10 averages. All right. We're going to get back to that group of averages. All right, let's go ahead and write that down so don't forget. Group of averages. All right. Now, notice every time I do hit enter in this thing, it is going to pick a new random sample of 30. So if these numbers change, don't freak out. You'll get the point as we're going through them. Now, one number that will not change is, let's say you're Mr. Newton and you're able to actually find the average of the 92 students because you have all of them. All right. So let's find out what that average is. Equals average, and we're going to find the average of all 92 students. All right, boom. Let's go ahead and see what it is. So the average ACT of the senior class that year was a 15.4. All right. But what if I, as Mr. Caproni, want to find the average of my 10 students' averages? So I'm going to find the average of the averages. All right. So let's go ahead and try to find out what that is. We'll go ahead and find the average of these numbers. And hit enter. And you notice that the average of my 10 students that they got was a 15.26. And the actual average of the class was a 15.40. Now, I want to talk to you about how important that is. Look at some of these numbers. Some of these numbers were a 20, let's see, 13, a 12. There's a few 26s in there. There's a bunch of like 15s, 13s, and so forth. So when you're looking down here, it's actually quite surprising that even though they all have a bunch of random different numbers, when you are picking 30 of them from the 92, the averages all come pretty close to being the actual average of the class of the 15.40. And more importantly, the average of the averages is almost exactly the same. It's off by what, not even zero point 0.2, so it's off by 0.14 of the actual. So between these two, looking at these two numbers, there's a difference of about 0.14. All right. When in reality, we're talking we had a huge gap of anywhere from 12 to 26. So the fact that this is so close is extremely important and it's extremely good news. This whole situation is what's called a sampling distribution. A sampling distribution is when you draw multiple samples from the same population and you find the average of each of those samples. Once you find the average of each of the samples, that becomes its own distribution called the sampling distribution. So before, where we had labeled this the group of averages, this group of averages actually has a name, and it is called the sampling distribution. And that is what this chapter is about. Now, there's a bunch of really interesting features about the sampling distribution, and it will become extremely important for us in the chapters coming up because it's what we're going to use kind of as a foundation for our probability questions and kind of a foundation for trying to prove certain facts in the world, correct or incorrect. All right. So we're going to go ahead and jump into the actual notes for sampling distribution. But just know, what is a sampling distribution? A sampling distribution is when you take a bunch of samples from a larger population, and then you take the averages of all of those samples to make up a new distribution called the sampling distribution. And it is not a coincidence that it is so close. The average of those is so close to the actual average of the class. And we'll talk about how likely that is that it's actually so close. Notice when I did hit enter, it went ahead and gave me a whole new list of 10 students, 30 numbers with new averages and a new total average. Obviously, the average of the class isn't going to change because these numbers over here are set in stone. But you can notice every time I hit enter, it seems like, let's see, yep. Now of course it's not doing it, but there we go. Every time I hit enter, you can see that it's giving me new groups every time. But look at these numbers and how close they are every time. Every time this sampling distribution has an average that's almost exactly the same as the real average. Look, 0.38 off the 0.40. It's almost exactly the same every time. Look, those are the furthest we got away. There's one that's 0.1 off, and that would be considered far. All right. So this is not uncommon. This will happen every time. So let's go ahead and start breaking this phenomenon down in our notes. First off, it says, rather than showing a repeated sample, we're going to imagine. So what's this doing? I just went through an example of sampling distribution that actually dealt with finding the mean of a group of numbers. But you can actually do the same thing with proportions, which we're going to do in just a second. And what would it look like for proportions? Well, I'll show you in a second, but it's going to be something along the lines of if I had, instead of each of those students collecting a bunch of numbers and finding the average of those numbers, I could instead have each of you guys flip a coin 100 times and give me what proportion of the time you guys got heads, like each one of you. So let's say Shalon tells me, hey, I got heads 51% of the time. And Kenyana said, I got heads 50% of the time. And I don't know, whoever else, Daniel tells me he got 49. All right. That would be doing the same thing, but with proportions instead of dealing with mean and standard deviation. So that's what we're going to look at right now. But instead of making you guys each flip a coin 100 times, we're just going to imagine what would happen if that went down, all right? So again, what would this be? If I collected all of your proportions, we would call that a sampling distribution, all right? So that is all the proportions from all possible samples. It's called the sampling distribution. All right. So we are kind of switching from looking at like what would it be like if we collect a bunch of numbers and do a sampling distribution to now the other type of doing a proportion distribution. So again, there are two types of sampling distributions. There's the type of sampling distribution where you collect numbers and then you guys would all report your means, and the sampling distribution would be the collection of means. Or it's where you do some type of probability thing and each of you would mark down your probability of success for all the trials you did. So like if you did it 100 times, how many times did you get a success? Say a 30% of the time or 40%. So it's the same concept. You guys each would take your own individual samples of the situation, and the sampling distribution would be the collection of your guys' final answers, your proportions. All right. So let's talk about if you guys were to actually do the example I said. If you were going to flip a coin 100 times, where would you expect most of you guys to fall? Well, hopefully you guys are all with me in understanding that if I said, hey, what's the proportion of heads you got when you did it 100 times, you would come back and say, well, most of the time I got 50%, or most of the kids in my class got a 50%. I would expect that to be the highest bar in the graph. If this were the number over here on the y-axis was the number of students that got this proportion, I would expect most of you to be right here in this range. All right. Now, there will probably be some of you guys that get slightly above that because you're just luckier. All right. And there will be some of you guys that get below that because you are not as lucky. All right. So that would kind of be our histogram here that we would be looking at. Now, after we go through that, though, as you get further away from that 50%, it would be rarer and rarer to see people fall in those ranges. So I'm not going to see many of you guys get 60% heads because that's going to be really rare. All right. I'm not going to see many of you guys get in the 40% range because that's going to be, again, very rare. And as you get further away, that is even going to get lower and lower and lower. Same over here, lower and lower and lower. So this isn't a new concept for us, that the further you get away from the middle, the less likely it is to happen. And in fact, if you notice, what do we have here? Oh, it's the normal curve. And whenever we are dealing with a normal curve, we always define it by two things. We define it by the mean, whatever is located in the middle. And in this case, that would be our 50% success that we expected. And we define it by the standard deviation. In other words, how far away is one standard deviation? We've talked before that it's at the inflection point. So, like, how far would this standard deviation be? All right. And that's going to create our normal curve that goes along with this. So let's see where this is taking us. It's saying we would expect the histogram to have the proportions to center at the true proportion. In our case, would be the 50%. And as far as the shape of the histogram goes, we would expect it to be, you know it, the normal model. All right. And it turns out that it is a normal model that's unimodal, symmetric, and the center is at what we would expect to be our probability of success. All right. Again, this is just a sampling distribution model. So this is just hypothetically what would happen. All right. And remember, the reason we wouldn't expect 50% from every person is because they will vary from sample to sample, just like how they did when we did the ACT means as well. They were all kind of similar to the same mean, but they did vary a bit. All right. So then it tells here to use the normal model, we need to specify the mean and the standard deviation. We'll put those in. So do we have an actual formula for the mean and standard deviation in this case? We do. The mean is just p. Like in this case, when we're talking about the mean in the middle of our graph, our normal curve, that will just be whatever p is. That for us in this case was 0.50, so that was easy. And then the standard deviation will actually follow this formula right here. All right. So that's going to be our standard deviation for a proportion sampling distribution. And that may seem intense, but again, we do not need to get caught in the muck of these formulas. All right. What you need to understand is the idea that if we were to do this scenario over and over and over again, that we would end up getting most people falling right where we would expect them to. And as we get further and further away from that expected proportion, the chance that students would get those numbers would be lower and lower and lower. All right. So will you need to memorize the standard deviation formula at all? Absolutely not, because the great news is that all of this is going to be located on your AP stat formula sheet. And in fact, just as a little FYI from last year, I know it's probably hard to read some of this, but there's no reason for me to make this big because number one, you'll have the AP stat formula with you. And I'll probably go ahead and link it at this point to your Schoology so you guys can bring it up anytime we talk about it. But these right here are actually the mean and standard deviation formulas for binomial and geometric distributions. So these are all your formulas from last chapter. Look, n times p is the mean, square root of n times p times q. And for the mean of a geometric distribution, it has 1 over p, and it has the square root of 1 minus p over p. These are the formulas we just had last chapter, so you don't have to memorize any of those. And we know that the calculator does all of this garbage over here for us. So you don't need to memorize any formulas. So stop freaking out that we're seeing a ton of formulas here, all right? Then for this chapter, every formula we mention in this chapter will be located in this section of the formula sheet. So I just mentioned to you that the mean of a proportion sampling distribution is just p, and that the standard deviation is this guy right here. So this is nothing fancy, all right? So if we look back at what this actually looks like as a normal curve, Remember, each one of these little tally marks should be one standard deviation away. So you would say, oh, this one's P, then this is one of those away from that. This is one of the two of those away from that, three of those away from that, and this is one going down, two going down, three going down. This is nothing new as well. We've looked at the normal curve over and over again. This is just that whole idea of doing here's where your mean was, which in this case our mean's P, plus the standard deviation. That's the formula for standard deviation this time. This is going to be plus 2 standard deviations. Again, this is nothing new. We've already seen all of this. This is just a picture of what's going on. We would expect most people that do this little scenario of flipping 100 coins to get 50% of them to fall in this range. As we get further and further away from that 50% mark, less and less students would flip that percent of coins. All right, we already talked about that. So when we get through all of that, and you know what, I actually think I'm just going to stop sharing the screen at this point. But at this point, we've talked a lot about what a sampling distribution is. And I know it's still going to seem really confusing. So I'm actually going to call it a day here with the video. I'll let that sink in for a bit. And then for the next video, we'll refresh on some of this stuff, but we'll also talk about how we're going to end up using this for questions and how we'll actually apply this idea. So what are your main takeaways from today? Your main takeaways should be this. What is a sampling distribution? A sampling distribution is when you're collecting data. That can be one of two things. It can either be a proportion or it can be like a grouping of numbers and then you find the average of that group of numbers. All right. It's when you do that a whole bunch of time, the collection of a proportion or the average of a group of numbers, and you get a repeat of all of those things. And those numbers make up a new distribution for you called the sampling distribution. And we have now also discussed the fact that when you find sampling distributions, all of these little individual samples where you're finding the proportion every time you do a grouping of 100 coin flips or something like that, you would expect most people to fall right in the expected value of that. So you would expect most people to get 50% for that, for the flipping of a coin. If we're talking about the ACT, as you guys saw, we would expect that most of those students who were collecting groups of 30 would end up with a mean ACT score of the 15.4 because that was the true mean of the whole group of 92. All right. So a sampling distribution is just when you're taking a whole bunch of smaller samples, all right, and where we are using those smaller samples and a collection of the average of those smaller samples to kind of compare it with the actual true mean. Now, spoiler alert, where is this all going to go? This is going to end up being used by taking a sample and finding the probability of getting that sample if we know what the true mean is. All right. So this is how we're going to essentially call people out if they're giving us false data. Like if I went out and said, hey, the average of the senior class for the ACT for 92 students was a 15.4. All right. And I don't know who to use. How about Kenyana? Goes out and tells me she went and sampled 30 students in the senior class, came back and said, hey, Mr. Caproni, I did my 30, and I found out that the average ACT score for a senior at West High with my 30 was a 22 on the ACT. At some point, we're going to be able to say, well, Kenyana, actually, the chances of that happening, you getting an average of 22, if the real average is 15.4, you're way too far away from it. So you did something wrong, you did your work wrong, or you're just flat out lying. You didn't take your sample, you gave me a number hoping it was correct, and you got it wrong. That's what this sampling distribution is going to be used for, is going to be able to look at specific samples and say, what's the actual probability that someone would get that sample? All right. So again, don't get stuck in the muck. I hope you watched all of this. I hope you let it all soak in, but I don't want it to consume your life. You will be okay. All right. And we're going to talk a lot more about this in the upcoming videos. So, again, everybody, Thanks for joining me today. I hope you guys stay fit, stay healthy. Have a great day.